So my name is Waleed, along with my team members Will, Joe, and Sam. We're part of the Underwater Autonomous Drifter project. Our sponsor is Boston Engineering, which is an engineering consulting firm based in Waltham. They deal with automation and control systems, along with research and development. And then we also have our advisors, Patrick and Josh, who were a big help for us. They were part of the first iteration of this project. So, does anybody here have any experience with data collection, specifically involving the ocean too? So this is basically what the point of this whole project is. Oceanography is actually becoming a very vital field in today's world, considering the current problems with today's world, involving like climate change and ocean warming. The best way to study the ocean is by collecting various data in various locations of the ocean. The best way to do that is to use an ocean map. So last year's iteration of the project was meant to design the interior and exterior of the hull. This year's iteration is to develop a charging system along with a mechanical stand that can serve as a storage unit for this drifter itself. Some of our constraints, or our biggest constraints, was that we had to make sure to keep down the battery weight and the charging system within the drone under 4 pounds, along with picking a mechanical stand that was going to serve as a storage and charging unit. Yeah, and then drifter batteries also had to supply sufficient amount of energy to run 10 days of full operation. So some of our design constraints was that we can't do any modifications to the hull since they were considered final. Charging time can't exceed more than 12 hours. The chi standard has to be between 5 to 10 watts, along with the receiving coils for the wireless component. Sorry to mention too, we were exploring 2 options to charge this drone itself, between wired or wireless charging. Now, for the wireless charging, the receiving coils, the most that they can get in terms of the temperature constraint is 4 amps. So that was one engineering constraint we had. And I'm going to pass on to the next slide to
Thank you, Ollie. So for our original proposed design, we had a environmentally isolated Pelican case housing a 24-volt battery that would be converted to AC current to run through a wireless charging system. The drifter would need to be integrated with an internal wireless power receiver that would transfer the energy from the external battery to the internal battery. And the system would be able to work on a ship that may not be accessible to AC power. It would also be able to be secured to the deck of a ship. For the wireless design, as I started to mention earlier, the 24-volt DC power, upon the request of this wireless receive controller here, it would convert the DC energy into alternating current to run through the transmit coils to produce the magnetic field, which would be absorbed by the receive coil and transferred back to AC current inside the drifter, where it would convert to DC to power the lithium charging circuit all inside the drifter. I'm now going to pass it off to Waleed to explain the mechanical stand design.
So for the mechanical stand, we decided to do actually a decision matrix based on around 15 cases, armored cases. Came down to the top 6 right here with PC 160, 1610 winning the battle here. The decision criteria that we had for the mechanical stand was dimensions, the cost, machinability, to be able to machine the case itself along with the weight. I put a heavy emphasis on the dimensions and cost though, since we had a budget. On top of that, I wanted to make sure we had ample amount of space for the drifter itself, along with a charging system to put within the mechanical stand. And this case proved to be everything we needed it. It's mobile, it can be safely stored on the ship, it can move off of the ship, and it offers everything we need. Now I'm going to give the next slide to Will.
Thank you. So to calculate the power consumption of the drifter, the largest concern was the buoyancy engine. which was controlled by a stepper motor. So to calculate the total charge that it would need to conduct a 10-day life cycle, we wanted to do 10 profiles, so one profile a day, and we needed to measure the total current and pulse width of initial and continuous steps of the stepper motor. So, and to simulate the depth of the ocean, we used a tensile stress analysis machine to put pressure on the buoyancy engine. And we measured the current and the pulse width at these different simulated depths with the machine using the oscilloscope where we could record the data. And for the calculations, we were given calculations by our sponsors for calculating the total amount of steps needed to reach certain depths in different bodies of water. And as you can see, this blue line is the worst case. It would require the most steps, so we used that for our data to make sure our system could fulfill that at least. And so in the end run, we used 10% initial steps, which were 50 milliseconds long, and 90% continuous steps, which are 9 milliseconds long, to calculate the total, just factoring in that once you're moving, that it would only be having initial steps when it's switching direction. And we calculated a total energy needed of 65 watt hours, which is about 1 pound of lithium-ion batteries. For the battery decision, we considered different chemistries, but we chose lithium iron phosphate because of their good energy density and substantial cycle life, and also their safety features. For the selection of the wireless charging controllers, we chose these TI chips because they were the highest power for Qi standard systems, and they also include features such as foreign object detection, temperature sensing, and also wireless communication abilities. And for the coils, we chose these Worth Electronics coils because they have a strong reputation in the industry and they're the strongest that we could find on the market that could handle the most power. When choosing these coils, we need to consider the exponential increase in temperature dependent on the current that we put through them. And also, we needed to maximize the quality factor, which to do so, it was desired to match the coil's resonance frequency to require a simplified design of the tuning circuit. I'm going to pass it off to Joe to show how we continue with this design.
All right, so after we found out the final hardware that we were going to use for our initial design, we went on to design the core circuitry that handled the transfer with the wireless transfer of power. By the time we finished designing these core circuits, we came to realize that the extent of supplemental circuitry necessary to achieve the voltages necessary to charge the battery not only were going to take too long to design and test, but also would push our power transfer efficiency outside of the range of that 12-hour charge time. So we met with our electrical engineering advisor, and we decided the best course of action to continue would be to instead move to an evaluation of wireless charging technology in general, basing our design on EVMs. We moved away from the Qi standard because it was deemed too low power. We moved to non-standard controlling circuits that were more powerful, could handle higher amounts of wattage. And this block diagram here reflects a design change. It's very similar to our initial design, with the only core difference being the technology we're using to actually transmit the power stress on the system. The results of that test are shown here. We tested the thicknesses of the hull material ranging from 1/8 of an inch all the way up to 3/8 of an inch. The hull is at its thinnest diameter, it's 3/8 of an inch thick. And as you can see, we achieved no coupling through the 3/8 of an inch thick material, despite the fact that we use the most powerful standard coils available on the market. Having eliminated wireless power transmission as an option, we refactored the design for a wireless wired design. This consists basically just of a standard off-the-shelf lithium charger coupled to the device using a waterproof connector. I'm going to pass it off to Sam to talk about the modifications we need to make while still staying within our constraints.
All right, so thank you, Joe. So, as you can see, we have a very simple design. We have a So because we couldn't touch the hull itself, the modification to fit the wired solution would have to be through a smaller component. So this is the sensor port highlighted in blue. The modification was very simple. All we had to do was make a threading that matched that of the connector. Once that was done, the wires from the connector would go through the port and then to the hull itself where the batteries are housed inside. Once done charging, before putting it back into the ocean to collect more data, a dummy plug is attached to the connector to protect the pins from any damage from the ocean. So the batteries inside, while they're charging, will generate heat and get hot. So they cannot get above 80 degrees Celsius, and to make sure they don't, we have to run simulation to calculate how much heat generation was made. With our configuration, we have about 175 watts going into the system, and 96% efficient batteries. That means we have 7 watts of generation between all the packs inside the drifter. So here's what we set up for the console model. The cube around that is the air, the drifter inside, and the packs stored inside the drifter where they would be located. And then specified that this is air, properties for aerodynamics. So as temperature changes, the density will change. That's making some natural convection inside the drifter. Even though, yes, the ventilation is very low, that had to be considered just in case it would lower the temperature inside. So for the actual heat transfer, we use conjunctive study, which combines both solid and fluid heat transfer interactions. Everything was set initially at room temperature. Qgen is at 7, and then radiation was, thermal radiation was taken into consideration from the outside of the hull to the environment, which is the room, and then from the batteries to the inside of the drifter itself. All the buoyancy effects inside that would deal with natural convection is done under laminar flow. So on the left is pretty much the expected result. Here you can see all the hot air inside traveling up to the top of the drifter as it's charging, thus making the top battery the hottest. And on the right, you can see the temperature curve for that battery. Steady state temperature after 10 hours is about 42 Celsius, which is much less than the 80 that was required from us. In reality, it should be even lower because that red line is when the battery stops charging because it's full. So what happens is the temperature gets to that point and then start dissipating since there's more Q generated. So the outcome of our project, we were able to find adequate housing for the drifter. We successfully calculated the amount of power needed to do 10 profiles as well as the batteries that would be adequate for it. We also successfully proved that the wireless configuration for this would not work. It's not feasible, and thereby moving on to a wired solution that we both design and would be adequate for this application while keeping a low budget. So as for our time spent, most of it in the beginning of the semester, in the first semester, was calculating the required power for it and any critical components going onto the wireless solution. In the second semester, the majority of it was spending making the wireless design, and even though that didn't work, it still showed us that we can move on to a now wireless solution. And for our bill of materials, our initial budget was $5,000. We only spent $700 of that. A good $500 was saved because the EVMs that we got, once we proved that the wireless was no longer of any use, we returned them for a full refund. So we would save $500 of that. And to conclude, I'm going to hand it off to Joe.
All right, so like many other groups, we face some pretty serious challenges along the way. First and foremost of those, since we have neither time nor the expertise to design a fully custom inductive charging solution, we were looking at standard solutions that were already on the market. Most of those, pretty much all of those, are designed for smaller devices like phones, small electronics, G standard especially. So finding something that was appropriate for our application, very difficult, proved to be impossible. Additionally, as far as the power estimation is concerned, the actual behavior, both the hardware and the software, the system that we're designing the charging unit for, not very solidly defined. We had a general idea, but the actual components and the specific way in which they would behave was not defined yet. So obviously, estimating the power for something that you don't know what you're estimating the power for or how it's going to behave, kind of difficult. Transitioning from a wireless to a wired design, because we spent so much time on the power estimation and the wireless design, by the time we tested that, found it was not feasible. We did not have very much time to refactor for a wired design, so we ended up having to cut some of the features like AC independence. Lastly, the console analysis proved to be somewhat difficult, again, based on not having a lot of unknowns, like what else is going to be in there, exactly how these batteries are going to behave. Future recommendations moving forward with this project. Currently, the batteries we have selected have individual balancing circuits within each pack, but creating a larger balancing circuit that can ensure each pack is charged consistently will increase the longevity of the battery packs. Secondly, if we were to refactor the wire design to use only a portion of the 8 pins on the waterproof connector, we could free up either remaining 6 or 2 pins to be able to program the device using SPI or I2C protocols, as opposed to using the unreliable Bluetooth. Increase reliability that way. Lastly, finishing that design for the AC independence of the wire design. We originally had considered AC independence for the wireless design, but refactoring for the wire, we would have had to change that up. Just a couple references we use for calculations. That's about it. Any questions?